Morning, everyone. Thanks for joining us tomorrow. This morning. I'm sorry. First, I will start with reminding you a few rules of our seminar, which I arranged for our convenience, and then I will introduce the speaker. So first of all, we keep your microphones and videos turned off. That's for safety reasons. Please, if you want to ask a question, there are two options to do so. So first, you may raise your hand in the Zoom. There is such a button below the list of the participants, and you may also ask your question in the chat, and I'll try to interrupt the speaker, or the speaker will notice this in the chat and will answer your question. So I'm very happy to introduce our today's speaker is Larissa Vertchenko from Technical University of Denmark. She's working in the group headed by Andrei. So Larissa is currently holding the postdoc position at Technical University of Denmark and works on design and modeling of nanostructures and their experimental characterization with focus on quantum optics and nanophotonics. So the title of the talk, near-zero index materials and for phone or low-loss integrated photonics, is closely related to Larissa's PhD project, which is going to be defended soon, as far as I understand. So I believe that our today's seminar can be considered as kind of pre-defense. So Larissa, please.
Yes, thank you very much, Anton, for the introduction. Today I will start with a brief, just 1 minute slide introduction of our group, so you guys can know us a little bit. We are from the Technical University of Denmark. We are the metamaterials and plasmonics group. We have some lines of research. We have sensing and biosensing mostly, water-based circuitry, and also material science and all-dielectric platforms. As Anton said, Andrei Vertchenko is our group leader and is currently also watching us. And I'm here mostly in the material science part and all-dielectric platform. And if you want to look for us, you can also find us in our group website. Now, to the actual presentation, brief outlook of what I'm going to present today. I'm going to show you what are the NZIM materials and their optical effects, some theoretical predictions we did with these NZIM materials, and then I'll move to a plasmonic NZIM material called titanium nitride. I'll show you our experimental characterization and its advantages and disadvantages on the field. Next, I'll move to dielectric near-zero index materials, a little bit different, and introduce some theory on bound states in the continuum and how we can combine near-zero index materials with bound states in the continuum. And at the end, I'll give you a summary and some prospects of our research. So to start, some motivation. I'm not familiar with the public, but it's important to show at least why we are doing this. So why on-chip photonics, why we are the photonics engineering department at DTU. We see these optical setups in quantum optics labs and also these D-Wave claimed quantum computer, and we see they are huge. They have problems with scalability. Also, all these components that are on the optical table, they are difficult to reproduce. So mass production is also an issue. And accessibility is another issue, because if we imagine how we travel around the world just to use each other's setups, because we cannot reproduce it in our own labs. So accessibility is a problem. And then we have photonics. And if you look at this picture, it describes everything. We can have a photonic chip on our hands. And in just this chip, we can have all the components we need. So this is our aim, our goal. but we do have some challenges. We have integration because we have all these components, detector, we have couplers, we have optical fibers, we have the whole circuit. We have unwanted optical effects, radiative losses, intrinsic losses, CMOS compatibility. This means that we need to do fabrication techniques that are compatible with silicon processing, because silicon is the main material in photonic industry, and we have thermal management. So all of these challenges, I'm going to focus today on mainly on the losses part. So what is ENZ materials? ENZ stands for epsilon-near-zero, and epsilon is the permittivity. And this means, if you're not familiar with material science, is that if you have a material block of any sort of material and we don't have any field on it, the charges will be randomly distributed. But if you have the electric field incident on this material, the charges will align them with the field. And how they will align, it's called the permittivity. And some examples of epsilon-near-zero material are silicon carbide and aluminum doped zinc oxide. We have, for silicon carbide, the permittivity 0 plus the imaginary part here, which is 0.03, and also 0.2. This imaginary part is important, and I will show you later, because it's related to losses in your system. Also, we can't say ENZ materials behave as ENZ for the whole wavelength spectrum. We have dispersion in these materials. Dispersion, for the ones that don't know, is the property where the permittivity is related to the frequency. So for silicon carbide, this material will behave as an ENZ at 10.3 micrometers, and for ASO at 1.6. Here in this picture, we have just a SAM illustration of ASO pillars that were fabricated in our group. And other ENZ materials that are very well known are, for example, silver and gold. We have transparent conductive oxides such as ITO, and we have transition nitrides, titanium nitride, hafnium nitride, zirconium nitride. And if you look at the permittivity curve on this plot, we see that at 0 in the real part, they cross the 0 part at the visible wavelength, at the visible range. So they are very good materials to work for visible and have these ENZ properties. But if you look at the imaginary part, they are quite high. And this will be an issue in the future when we discuss about these materials. So first, I will consider the lossless case. And historically, if you look at the papers about ENZ materials, you see that they have exotic and very fantastic effects, but you need to be in very low losses for this to happen. So the first property is that we have strong electric field in ENZ materials because of the conservation of the displacement field. Also, this is an impressive property, is the enlargement of the wavelength. If you think that the wavelength is related to the refractive index, which is also related to the permittivity, when we calculate the wavelength inside the material, we see that at the ENZ material, the wavelength goes to infinity. And this is something that we can't really relate, because what does it mean to have a wave that goes to infinity, a wavelength? So it's very strange. And also we have another property that is the phase distribution. It will be constant. And this is very important for quantum communication because it means that the signal will be coherent. I'll talk a little bit more about this later. And if we put all of these properties together in the field equation, we'll see that the field is actually static spatially, while it maintains this dynamic oscillation in time. And this is very interesting property because if you think about designing cavities, optical cavities, for example, it means that we can have different cavity designs, different shapes, and they can have the same eigenfrequency. So epsilon-near-zero materials bring flexibility to design of photonics circuitry. So one property that comes out of this enlargement of wavelength is something called supercoupling effect. So here to illustrate, we have an incoming field that is in air, for example, and reaches a slab of refractive index of 0.5. So we expect that the wavelength will be a little bit larger. Also, if we have n equal to minus 0.5, we have negative refractive index materials. We know that it will have the same effect, but phase velocity to the other side. But now, if we have a material that has n equals to 0, this is the picture that we must have in our minds, is that this field oscillating in time, but completely uniform. Now, why is this property important here? The supercoupling effect states that if we have a waveguide, a simple waveguide with air or any trivial material, and then we have an ENZ channel which is just distorted or full of imperfections with edges and so on, light will not be able to propagate to the other side without suffering reflections, and basically because of impedance mismatch. But if this channel is filled with ENZ, the wavelength is so large, it won't be able to feel the effects of these small imperfections. And also, it has this property of impedance matching. I didn't put the calculus here, but it's very good for that if you have the transition between big channels to small channels. And this is, we can observe here in the simulation where we have the incoming field and it passes through a narrow and fully distorted ENZ channel, and the outgoing field will be fully transmitted. So, and this was experimentally verified by Nader and Getter's group, where they used in microwave regime, and we can see from this small yellow part here, this would correspond to the ENZ part. Another effect that is interesting is how we can combine quantum emitters and epsilon-near-zero. Here we have a dipole as simulating our quantum emitter, but this is the classical part that we can simulate. And if we think that we have a dielectric inclusion in this ENZ environment, by changing the dielectric inclusion's size, we can tune it to have a resonance behavior that will couple to another emitter in the other cavity. And that's what is depicted in this picture below. And we can also calculate this, this is collective decay of the charges by this, this formula here where we use the green functions formalism. This means that if we have a dipole, and for example, it's in the ground state and it goes to excited state and goes down, the photon emitted by it can go to the other cavity and do the same with the other dipole. And there will be a transitional state where we have this synchronicity between them. And this can be calculated by this equation. So our idea here is to combine these two effects, the supercoupling effect and this coupling between dipoles. Because usually when we have dipoles, they have to be very close to each other in order to communicate. It's a question of nanometers. Here, the supercoupling effect will make this possibility to make them further apart from each other. And then with that, we can put more logical operations in our circuitry, in the chip, so we can operate with the quantum emitters properties. So here is the simulation result we got. We have a dipole, and outside is NZIM material with very low losses that I must emphasize. And the channel is also NZ, and you see it's fully distorted. And when you look at the signal, at the electric signal from the both cavities, you see that they are almost the same. And this system can be expanded to more and more cavities. And when I say more cavities, you can also think by putting more emitters in each of these cavities. And then if we look at the phase of the system, you see that it's completely constant. And this is very important. I'm going to talk a little bit about the phase later. So this is the collective decay rate I calculated for two emitters that are, for example, in this system, and also the lamp shift. The lamp shift is a shift in frequency when you have the interaction between emitters. And you can see from the collective decay rate that it's maximum when the plasma frequency is the same, the frequency is the same as the plasma frequency. For materials, it means that when they are at the plasma frequency, they are at the NZ regime. And we have the highest collective decay rate here. It means we have the highest coupling. And just a comparison, if we were to use air in the system instead of NZ, we see this black curve here. We see that ENZ is way superior because the electric field is higher in the material than in air. So it's a good material for distributing signals in a communication network. About the phase property, so we have something called coherence, and for those that don't know about it, about quantum mechanics and so on, it's a property that the waves are able to interfere, if we say it qualitatively. If we have, for example, interferometer, a microscope interferometer here, and we can move, we have the laser source, and we have a beam splitter, and when we put the beams together, they will have this interference pattern of fringes. But this happens because the wave is coherent. This means that it has a phase, the phase is well defined between the waves, like in this, in this picture here. But what happens when we are dealing with photonics is that we need to consider matter. We need to consider the medium. And what the medium does is it messes up the phase, because we have reflections, we have absorption, we have scattering, and all of these effects will give your waves these random phases distributions, and this will make your state of your system decohere. So this is important property, because if we think about quantum mechanics or quantum optics, for us we have in classical bit that is 1 or 0. But if you go to the quantum optics part, we have the superposition of states. It's the superposition of states 0 and 1. And if a state interacts with the system, if this qubit interacts with the system or the environment, what happens is that the environment will be able to do this measurement in your system before you are able to detect it. And by doing a measurement, it means your system will collapse in one of the states. So this is very problematic, because it means it decohered before you were even able to make a measurement. So we need to avoid these random processes done by the medium. And one way is to use these ENZ materials. Because if we calculate something called the coherence length or coherence time, they are related to each other by this equation. It means that it's the length that the wave will be able to propagate without suffering decoherence. So we can, if you calculate it, we'll see that for silicon carbide, for example, you will have very long coherence length for 1.4 millimeters. To compare it, we have metals, for example. If you use metals, the coherence length of metals is in the order of 10 nanometers. So it's so small that you cannot even operate with the state before it decoheres. I must emphasize that you can say have dielectrics. You have silicon, for example, that has a long coherence length as well. Yes, that's true. But we have also other disadvantages in using dielectrics because, for example, we have big footprints that can mess up your signal as well, and it's very difficult because of corners and so on. So in our case, the NZ is will make the circuitry coherent in, for example, this radius of coherence. That's what we call that inside the circle, everything is coherent. Thus, quantum properties will be preserved. And also, because of the supercoupling effect, we can have all these emitters interacting with each other. So this is something that will be outstanding to be fabricated. And as I told you about the dielectrics, if we have silicon, for example, and it's not in an NZIM material, the emitters, even though they can transmit coherent light, they cannot communicate with each other because the dipole-dipole interactions need really short range distance. So this is what I was going to talk about in our theoretical approach of NZ. I think it would be good just to stop here, for instance, to ask if someone has any questions so we can continue. Okay, I see one hand.
Yes, I'll just switch on the sound, Maxim.
Yeah, thank you. So I have two questions, basically. One of them is about slide 16, where you're discussing slide 13, sorry, where you're discussing the issue of synchronization. So which system specifically did you simulate? You just put, you know, in CST epsilon equal to 0 and that's it? Or you considered some specific structure?
No, so this system we simulated with a dipole, and we use console to simulate the electric field, and from the electric field we calculate the Green's function, and from Green's function the other properties like the collective decay rate and NZIM shift.
Yeah, but, I see. But what about the medium?
The medium is simulated with silicon carbide properties. The dispersion curve of silicon carbide.
Okay, good.
And yeah, so, it's not just putting n equals 0 and that's it.
Okay,
yes,
got it.
Yes.
And then the second question about slide number 15. So you are comparing basically here in the bottom of the slide, comparing two curves in ENZ and air. But I see that the difference is not like order of magnitude, is just maybe 50% or something like that. So the maximum height of this black curve is around 30, let's say. And in ENZ, you have this enhancement factor like 50. So not even 2 times.
Yes, but
so the question is the following: if you are dealing with some realistic ENZ material, let's say somehow structured, then people know that there might be some spatial dispersion effects which manifest themselves in the limit of large wave vectors. And then if you expand the field of dipole, then you necessarily have this large K, and then there might be some, you know, corrections due to the material periodicity, due to the material granularity.
Mm-hmm.
So this raises a question whether indeed this ENZ structure is so advantageous to the air.
Yes. So to answer that, if you remember my outlook, so I'm giving you more like a historical view of my PhD project, and this was the first phase. And if you remember, I told you about the losses. Here, losses are very small. But if you consider NZIM materials like titanium nitride, which I'll show you later, the losses are really high. And these effects will all be lost. Then that's why we will go to dielectric platforms later, and I will show you how it will behave as an NZIM material.
Okay, thank you. So let's wait till the second part.
Yes. Okay. So now, as I was telling about this, there is something we must emphasize here in order to continue. And that's actually the discussion that was pointed out. We have something called near-zero index photonics, when we have the refractive index that is actually near zero. And this is something that we must differentiate, because we have the refractive index, which is the square root of epsilon. But if you have lossless case, ENZ and NZI will be the same. But if you consider the losses, N might be bigger than 0 and not even near it, and then they will be different. So for example, we have titanium nitride, and that has epsilon, which is 0 plus I4. And this gives an N of 1.4 plus I 1.4. So you see, titanium nitride is a ENZ material, but it's not a NZI material. And because of these losses, all these effects that we were discussing would be killed. And this is actually the main challenge of ENZ materials. It's very hard to find this such homogeneous material that will have low losses. And silicon carbide is being one of them that, but the issue is that silicon carbide wavelength is 10.3 micrometers. So we have another good candidate that might have low losses is ITO. ITO is for 1.5 micrometers. So there are some options, but these effects to happen, I have calculated, and the imaginary part of epsilon should be less than 0.1. Okay, so to talk about titanium nitride as an epsilon-near-zero material, if you're not familiar with it, it's a very well-known material. Actually, it's used for industry with this yellowish color because it's very hard for these construction things that it's for drill. I never remember the name of these things. It's used for biosensing because it's chemically stable. It has a high melting point, and it's good because this makes it CMOS compatible. And there, I think you have seen this, you all there. It's actually used for coating the churches now. They are changing the gold for titanium nitride. So it has a permittivity curve of like this plot, and we see its ENZ point here. But again, the losses are really high. So our idea was, let's put this material, which was a 100 nanometer thin film of titanium nitride, under low temperatures. And low temperatures, I mean really cryogenic temperatures. We reach 1.5 Kelvin. And we wanted to investigate how would the losses decrease. So we did this by a method called the transfer matrix method. It's where we consider each slab of the system a matrix, and we have the reflection and transmission coefficients, and also the propagator. And from that, we get the permittivity curve by fitting all these terms in the Drude-Lorentz model. If you're not familiar with Drude-Lorentz model, it's a model that will describe the electrons in your material. And we have this term that corresponds to the free electrons part. So we have the plasma frequency and damping. But we also have the second term, which is called the Lorentz term. It's responsible for intraband transitions inside the material. To do this fitting, we basically change more the first term, because we know that it's the term that will influence phononic waves more. So basically the energy goes to phonons in the system. So when we decrease temperature, it will get better. So we did see this improvement. We see that ENZ point in the real part did not change much. but the imaginary part goes down quite a lot, goes down to 1. And but still, I must say this was, of course, disappointing as a PhD student looking at this, but it wouldn't be able to perform what we were expecting it to for the NZ networks. So, and we can even compare it to silver, for example, which is quoted as the best plasmonic material. And we see that silver is still better in terms of plasmonic properties. But one thing that we notice is that when we look at the refractive index, the imaginary part of the refractive index, which will be responsible for penetration depth in your system, is actually lower than silver. So this means that it might have good local properties in a sense that you can penetrate more in the system. And also, I will emphasize that I'm not saying titanium nitride is not good for anything. It's actually good for example, nonlinearities. We have seen that nonlinearities are enhanced when we have the NZ material. But for transmission properties, as we expect for NZ networks, it is not good. So we have some options of materials, and these options will involve effective medium theory approach. Effective medium theory is basically putting combinations of material together and saying they have these, they will behave as having these uniform effective permittivity or effective refractive index. So we have some materials, for example, trenches of dielectric and metallic layers. We have, for example, silica and silver, or we have even very complex materials that will behave as low index. But even if we combine these materials together, they still have some losses because of the conductors. And it might not be less than 0.1. The cases that is less than 0.1 is actually very hard to fabricate. So this is a challenge when using these kinds of materials. And we do have research on that, but it's very hard to fabricate such structure that will behave as an ENZ with low losses. So then I'll move to this last part, which is the near-zero index materials and all-dielectric platforms. So by all-dielectric platforms, I mean photonic crystals. Photonic crystals can be made of pillars. It can be made of membranes with holes, for example. And when we analyze the band diagram of photonic crystals, the band diagram, for those not familiar, is the frequency dependent on the momentum. So we have in the reciprocal space this ky and kx instead of having coordinates, spatial coordinates, and we have the frequency. And there is this particular point called Dirac's triple point, where we have this cone shape structure, we have this cone shape dispersion, and we have another mode here, which is the triple mode. And when these modes are together, we have a dipole and a monopole here, 2 dipoles and 1 monopole. When they are together in this triple point, they will behave as an effective medium with effective refractive index close to 0. And you might have seen these cones before on graphene, for example, but they don't have the triple point. And in graphene is not at the gamma point as well. This is actually at the gamma point. The gamma point is the center of your Brillouin zone. It's the center of this plot here. And what is good about it is that then we overcome the losses of the intrinsic losses in our system. And you can say, okay, problem solved. And I simulated here, as the discussion before, the supercoupling effect for a pillar platform, a silicon pillar platform, where I investigated the triple points, and then we can see that we have a dipole here. In this green arrow represents a dipole, and then outside is another photonic crystal that I calibrated to work as a mirror. It means that no mode will propagate inside this. And when we look at radiation, it's really intense in the channel, as it is expected for NZ. And also it will propagate all the way to the end. I didn't put the plots here, but it was the same magnitude. And this you cannot have with air. Even if you have a lot of mirror resonances together, you won't have the same result if you have the supercoupling effect. Also, phase here is preserved. You see, phase is uniform. This you never have in another material if you have mirror resonances trying to put together. Okay, and I think to move forward, maybe again, I'll wait to see if there is any question.
So Larissa, may I clarify something?
Yes, sure.
So again, you have somehow connected your optical properties in the real space with the band structure in the K space. Could you please again clarify the role of those three bands you have here, maybe two bands, okay? And what is a monopole, by the way?
Okay, so here in this system of pillars, we are exciting mirror resonances. And the mirror resonances corresponds to each mode of your system. And these are the modes that are described here. And the first cone represents a dipole. The middle one will represent another dipole, for example. And the last one will represent a monopole. Is it more clear or?
No, basically not really clear. So when you're talking about mirror resonances, you mean that, okay, your single unit cell has kind of resonance itself. But
Yes.
when you build up a lattice, you have this lattice effect from which you obtain the band. So usually, so for small particles, we usually expect electric dipole, magnetic dipole, and with their different orientations with respect to your plane
Yes.
geometry. And from those bands, you may expect that they will form some, so from those resonances, you may expect that they will form some bands.
Yes.
So still unclear what are the bands responsible for, well, resonances, exact resonance responsible for those branches you show. And again, what is the monopole? So I wouldn't expect that there would be such a resonance. What does it mean, monopole?
Oh, okay. The monopole here is the field is mainly concentrated in the pillar, and that's it. And you see how the electric field here is has this rotation.
But
Just
could
like,
it be a vertical magnetic dipole, for example?
it could be. But here, each band diagram depends on polarization. So I think I didn't mention that. So here we can have the system with TM or TE polarizations. So each band diagram depends on the polarization of your system, if the electric field is aligned with the pillars or if it's orthogonal to the pillars. So these excitations depend also on the orientation of the pillars. And when we solve the eigenfrequency of your lattice, you'll find that there is this point that they all encounter each other. So in this lattice, for example, very close to this triple point, we have one monopole, we can see the one dipole, and I didn't put in the picture here, there is another dipole, which is responsible for the other band that is below. And yes, I don't know if that answered much Yes, exactly. The monopole is the zero. Yes, that's right. Someone wrote here. Monopole is
So
zero.
so we have guessed this. Pavel, just a second before you ask, and so you're showing the dispersion, the real parts of the K and the frequency. I'm wondering, so since you are dealing with gamma point here, you may have leakage, and those are leaky modes, and also you have to maybe show what are the Q factors or the imaginary part of your frequencies or.
Okay, so that's very nice because that's actually my next slide.
Okay, then Pavel, do you want to ask something? You had a hand. If not, then Roma is asking a question. Roma, please.
Yes.
Yes. So I just wanted to clarify about the next slide. So you have this kind of Bragg mirrors on the next slide with two dipoles.
So the next slide?
Yeah, the next slide. Yeah, here.
Oh, okay, here.
So these are like mirrors only in these two dimensions. I mean,
yeah.
So the radiation can leak out in the transverse, like
yes.
normal to the side.
Yes, you are all moving to my next slides.
Okay, thank you.
Okay.
Yeah.
So this was actually, so if you think if you put yourselves in the head of a PhD student that was trying to understand this stuff, we had to do the basic stuff first. There was the 2D dimension first. And then after we found the solution, again comes challenges, and that's what you're all mentioning is the losses. And now here we have the radiative losses. It means that radiation will go all to the sides, even above, below, and also around it. And even if you put, for example, substrates for here, we can see that it leaks to substrates. And if it's pillars are very tricky systems to work with because radiation really goes inside the substrate. And there have been some solutions for it, especially from Eric Mazur group in Harvard, that they make this complex structure where they use mirrors with gold, for example. But this is not very practical, and it's hard to fabricate, hard to realize, and hard to integrate. So what should we do next? And that's also what you all are discussing. And I think some people there, I saw some familiar names, know this solution already. And it's the bound states in the continuum approach. These states, if you think about the particle in the box system, we know that the solutions to Schrödinger equation gives us discrete energy levels. But then if we modulate this well, we will see a solution that is actually in the continuum, but is very well confined in your system. And then we have two types of bound states in the continuum. We have one called symmetry protected bound states, and it's related to the symmetry of your system and at the gamma point. So we can see from this bottom picture here that it relies basically on the symmetry of the mode that is confined in your system. But we also have something called accidental BICs or trapped BICs. They are moved away from the gamma point, and they are a result of interference, destructive interference happening. And these you can, it's actually easier because you can calibrate the thickness of your system, for example, a membrane, or the height of the pillars, so that they can have destructive interference. And then the radiation would be mainly inside your structure. And here is an example that you can calculate the Q factor of your system. Here we have something that is not on the BIC regime, and here we have the BIC regime. And then if you calculate the Q factor, we see that it diverges at the BIC. It means it goes to infinite, and then everything is well confined in the system. The system here is a system of trenches in silicon. I remember this was fabricated by a group in collaboration with your institute. So just an illustration of this, we have confinement in the vertical direction of this membrane, for example, but it doesn't mean that the waves can't propagate in plane. And here we can have this system like this, where we have propagation in plane, although the out of plane is completely destructive interfered. So here it was experimentally verified. If you are at the BIC, for example, you can see this cross here in a square lattice of holes, and this corresponds to the BIC and the waves that are propagated in plane. And out of this mode, you don't see anything. And they are used, for example, for sensing, for biosensing, because the well-confined field will be able to interact more with biosensors, with analytes, with biomarkers, and you give better sensitivity to your device. So this was the solution. We saw, okay, let's try to do this near zero index materials with bound states in the continuum. It was actually at the same year proposed by Shanhui Fan and his group, and they proposed this membrane. And what is difficult about combining these two effects of having a near zero index material, meaning that we need to have the right modes excited in your membrane system and also to have bound states in the continuum, is that you need specific shapes. Here, for example, they designed this flower-shaped material. But you see, this paper was theoretical for a reason. It's very hard to fabricate this. And it still hasn't been. I've talked, we have a collaboration with Harvard. They were trying to fabricate this. And it's very tricky because the edges of your system. But you see, if he theoretically analyzed it, and he got the triple point here. And he saw that they would be able to have bound states in the continuum with near zero index behavior. The bound states in the continuum I didn't put in this picture, is in their paper, but they analyzed by looking at the Q factor of your system, of their system. So what was our idea? People are trying to find a homogeneous structure to fabricate and get low index materials. But it's very hard. So we decided, let's make hybrid systems instead of making just a uniform shape. And the hybrid system comes like this flower shape here. Small holes, and if you look at the lattice of the photonic crystal, it's actually a hybrid of triangular small holes lattice with a square lattice of big holes. And this white square is actually the unit cell of our system. So here I projected the band diagram of this system, and you see we are also able to reach a triple point. What is interesting in this system is that this system is asymmetric. So we don't have a circular cone. We have this very long part here in the y direction, while very short in x. And we see the Q factor has this divergence here. Please don't mind the numbers. I forgot that to change. It was multiplied by some constant, but it was in the order of thousands. I can say that. And but we see that this divergence here that is called the trapped BIC. As I mentioned, this was a collaboration between us and Professor Eric Mazur at Harvard University. We have fabricated these samples. It's a silicon membrane on glass. And if you're wondering about the size of these samples, is around some 200 nanometers, the radius and diameters and of these holes. So to look at how the sample really looks like, it looks like this. It's actually very beautiful to look at. And it's a 200 nanometers thick silicon membrane on silica. And the characterization of this system is based on two parts. We have the K-space visualization by a CCD camera, and it's used, we measured by scattered signal, but we also see the transmission signal in a photodetector. And these two parts will correspond to the full characterization of the sample. So when we look first at this K-space by the scattered signal, we will see, when we scan all the wavelengths, we will see three special pictures. So the first A and C pictures, A and C, corresponds to BICs. They have these straight lines here. And the big picture actually corresponds to the triple point. And this is the simulation of the plane. I'll go back here, of this middle plane here, where they intersect. And if you see the black part here, will be the white on the other slide. And this is the plane where they intersect, and it corresponds to this line shape here. This picture is kx and ky, kx and ky, if you think about the axis. But what about the other two BICs? We cannot see them from the band diagram. But if you remember, I showed you the picture of this experiment where they have the cross here. But we don't have a cross, we have only one line. Why is that? It's because our system is asymmetric. It means it has one BIC it has a BIC in one direction, but it doesn't have a BIC in the other one. So that's why we see only one line here. And this is very interesting because now we have only control, we are controlling the Z direction as in confinement in the membrane, but we also control in the in-plane direction. We are controlling the radiation that can propagate in plane by putting the asymmetry in the photonic crystal. These BICs are called separable BICs. And this is actually very new. They haven't been studied a lot. We have some studies in Soliacic's group, but it's very hard to achieve such systems. And it's very new. So these are our results from the first part of characterization, where we look at the K-space to check that they are there in the samples. And then to have a finer characterization, we look at the transmission of the signal at the photodetector. And we see two very small dips here and a large one. This dip corresponds to another bands that intersected later on and they reproduce some absorption and dip here, but we are interested in these very fine lines here. These very small and thin lines represent the BICs, and when we calculate the Q factor for each of them and we change the angle, we get these two plots here. And we feed the data and we see that they are actually diverging. So this is the actual confirmation that we have the BIC. Because when I looked, I didn't put images here, but when I looked at the transmission, for example, of this broad dip here, you would see that it didn't change much. So the Q factor was very constant, this one. But this one, we see a big change. And you might say that 2,600 is not a very high Q factor as it has been reported for other cavities and so on. It's true, but you have to think that this system is actually on glass, and substrates break symmetries, and it's hard to have high Q factors on them. Besides, we didn't have enough precision to go further here. So that's one thing. So we might have even bigger Q factors. And another thing that I must clarify is that we are not thinking about making a cavity. We are thinking about making a high Q system in the sense of waveguides, so we can have the supercoupling effect. So now I'll move to the prospects of my PhD project, and let's put this system inside a waveguide. And what happens if we put the system inside a waveguide is that we have phase constant, and this is great. We also have, so this is the phase, this is the field profile, and here the polarization is in plane, electric field in plane, magnetic field out of plane. And we have the electric field in this material. It was in a collaboration with the University of Savelev, Denmark. It was calculated to be 8 times higher than common waveguides. And here the transmission properties are also very good, as well as Q factor. So the idea now is let's make high Q factor waveguides, not like cavities, because do you know that cavities, they also have other geometries that can have higher Q factors. But let's make high Q factor waveguides that will help with the propagation losses in the systems of in photonic systems. I didn't mention here, but we also, okay, this is the same picture of the waveguide we actually fabricated. It's our ongoing experiment. We have here the mirror part, and we have the near-zero index part here. And if you want the full description of it, it looks like this. This is a membrane. We are trying to make even better high Q factors by making symmetric the system, where we have a complete full standing membrane. And this tip here is used for coupling radiation. And here inside is the medium. So another thing is that we are also already doing experiments with quantum dots in this system, because we know that it will also change the dots properties. So now I think I will give the conclusions. So I'll show you that NZIM materials and near-zero index materials can provide a great platform for quantum photonics due to preservation of coherence. Also, intrinsic losses are challenging for NZIM materials, and that's why we moved to all-dielectric platforms. But we do have radiative losses, and bound states in the continuum can overcome that, and can give exceptional transmission and light confinement properties. So with that, I'd like to say thank you. I'd like to mention our group again, because this was a very challenging project, and we have collaboration with Harvard, with SDU, and also this new center that I'm now working in is the nanophoton. So if you want more information, you can go there. There is also my email and our website if you need information or if you want to contact us. So, okay, I can answer any questions now. Thank you.
Thank you very much, Larissa. So colleagues, please raise your hands if you have questions. Roma, please.
Yes. Yeah, thank you for the talk. So I have a question about, I think the last slide about the waveguide.
Okay.
So there are kind of,
this one?
Yeah.
Okay.
There are, let's say, conventional photonic crystal waveguides.
Yes.
That work below the light line. So by design, they do not have any radiative losses.
Yes.
So you don't need to overcome this by this bound state in continuum. So I wonder, like, what are the advantages of this design?
Okay. So this design was used because we need to also integrate other components afterwards. So although we have these waveguides, we also need to integrate it with some other materials. And also we wanted to analyze the signal incoming and outgoing. So it was just to facilitate the design of putting everything together here for the fabrication guy. I didn't fabricate this, but it's just to move the signal inside and outside. It's not really on the waveguide that will matter here, that these mirrors will matter. It's muted. I don't know if he has questions or not.
Probably not. Rama?
He doesn't have the microphone on.
But probably Rama is okay with the answer.
Well, I don't know, actually. So what is the problem with integration if you use this conventional photonic crystal waveguides? So you just have a little bit different design?
No, it's because if you think about other integration approaches with photonic crystals, you have cavities that need mirror part. They are like a simple defect on the whole mirror part. And we need to also implement other waveguides here, for example. And but this was mainly that we can guide the signal here in and out. We need this mirror to guide the signal in and out and have a reference if we don't have this. We also made waveguides without the zero index part, so we need to compare them. It's more a matter of comparison than just putting this and say it will work. So it's because the system is very sensitive as well, so we need to analyze all this stuff. That's why this is really the beginning. This is actually the first step that has been done so far.
Okay. Thank you. Maybe I can ask another one.
Yeah.
So it's just I was a bit lost. So first you told us about NZIM materials, and then you moved to these BIC structures. So what they're made of? So there is no about NZIM materials in these structures.
So okay, so that's why I put this slide here. Oops. It's because the NZIM materials, as we know, like titanium nitride, they have very big losses. So when ENZ can be the same as near zero index is when losses are very small. So the ones we analyze, like titanium nitride, we cannot say they have near zero index, but they are epsilon-near-zero because if you look at the permittivity curve, it will pass at the plasma frequency. They have the plasma frequency, and that's the epsilon-near-zero, but they are not near zero index. And here we move, so after titanium nitride, we move to all the electric platforms. And we are using, instead of an ENZ material that has the permittivity curve passing zero, we are using silicon, and silicon doesn't have the permittivity curve moving in zero. But we use the effective medium theory approach, and by effective medium theory, we calculate that if we put the pillars, they effectively will have the refractive index close to zero. So it's an all-dielectric material. And that's the same for the membrane case. In membrane, we also using silicon, and that's the material here.
Yeah, okay, I understand. So you just talk about these structures, photonic crystal in terms of permittivity. Okay,
yes.
Thank you.
Okay, colleagues, any more questions? So I'll ask one. So for quite a long time, people are talking about the effective medium approximation, and there are many specialists here in the list of the participants of the seminar about that. So I know that your scientific advisor, Andrei Vertchenko, has shown experimentally that this effective medium approximation doesn't basically work, since they have taken a multi-layer structure, and the optical properties of the structure were strongly dependent on the layer they used to terminate the structure. So when you're talking about this, and of course the spatial dispersion and all the stuff. So when you're talking about the effective medium approximation, to what extent do you appeal to it?
So here it's a little bit different because effective medium theory in such materials in this photonic crystal approach, it depends on the modes you excite. And we are close to gamma point, And if the modes we excite are linear around gamma point, we can calculate the effective medium. But it was shown by Shanhui Fan and his group that, and also Siti Chan, that if I were, for example, to find instead, because you can find triple points that actually won't behave as effective near zero index materials. And these triple points are related to the effective medium. So some modes combined won't behave as effective medium theory. So there are exact modes that we need to find to have this property. And also, if we say about the term, sorry, I think someone in the chat. Exactly, it's effective mode index. It's my supervisor is now adding something to the chat. So we find it's not the effective medium theory that you are used to, but if you are linear close to the gamma point, you can say you have an effective mode index. I think it's kind of, I might have how to say it, relaxed a little bit on the terminology on that. But and the way they did it is they actually calculated for pillars, and they showed that if you work with effective medium approach, it will correspond to the same as a homogeneous structure with the same refractive index. That's how they did it. And about if the system is limited in size, of course, it would change the band diagram, because you're mainly introducing effects on the edges, for example. And but here we make sure that we have a large enough system to characterize. I don't know if I answered.
Okay, so you are talking about the group index, and your near
Yes.
zero behavior is just your flat band at some point, for example.
Yes, exactly.
K = 0.
But the thing is that you need to have these modes intersecting together, because if they are not, the effective mode would be different. The effective index will be different. So you need them intersecting.
Okay. Okay. Colleagues, do we have any other questions? So if you don't mind, I'll ask now. Okay, Andrei Lavrenenko, Roma Savelev. Okay, so let Andrei go first.
Yeah,
Andrei.
Question is, I simply ask Larissa, please give the numbers for effective mode index.
Okay, effective mode index here is 0.02, close to gamma. It was calculated to be 0.02.
Okay, Andrei, any other comments?
No, it's okay.
Okay, then Roma, please go on.
Yes, thank you. So there was a slide where, I don't remember which slide, but there was a slab of this photonic crystal, and experimentally it was shown that some these kind of waves were excited in 4 directions.
Okay, the
and there
side
was some
waves.
kind of spin polarized.
Yes, that's yes. I'll show you this one.
I don't really understand. So in this scheme, it seems that the wave, so this external wave is incident at normal angle. Is it
so,
right?
the wave here is coming from the normal here, yes, and on the top, if you look at the top view,
So
and
why do you get this?
It's able to excite Bloch modes in the system, Bloch waves, and they go to the sides. That's what it means. I didn't want to go further into Bloch waves because I really don't know the audience, but that's what it means. This system.
Okay, and maybe also about this slide, for example, in this kind of system, systems. So what is typically the size of this structure, transverse size, and what is the size of the incident beam?
Okay, so I can tell you, I don't remember in this paper, but I can tell you in our structure, because we measure something similar. In our structure, the holes here, are you asking about the holes? I will give you. I mean, in general, just. I will give you everything then. So the holes are around 200 nanometer diameter, 100 nanometer diameter. The full structure was, I think, 500 micrometer in the side. So you think about like 500 micrometer square here, and the thickness is 208 nanometers in the E of silicon, and it was on top of silica, and the beam spot size, if I remember correctly, was around 1 micron. So we had several optical setups with a good objective to make this spot very small.
And if you measure these resonances, you showed some quality factors.
Yes, these ones.
Do they depend on the size of the beam or
no, they shouldn't. They shouldn't, because I mean, of course, if you put a beam that is bigger than the whole structure, you also have reached the medium outside. But if you are inside the system, since the system will have the effective mode, the effective refractive index, so it shouldn't depend on the beam diameter.
Okay, thank you.
Okay. Okay, it seems that we do not have any more questions. So before we finish our seminar, I would first of all like to thank you all for the participation and asking your questions and listening to this. Very nice talk. I have to announce that the next seminar will be given by Dr. Sergei Makarov at 10 a.m. next Friday, April 24th. He'll be talking about perovskite, nano, and micro lasers. And so after all, I propose we can thank our speaker. If you switch on your microphones, we can clap our hands and thank Larissa for that. So Larissa, thank you very much. So thanks to everyone for joining us, and looking forward to see you next time in a week. Larissa, thank you very much for your very nice talk.